Hello everybody, my name is Giuseppe Carleo and I'm the head of the CQSL, the Computational Quantum Science Lab here at EPFL. Today I'm happy to introduce you to the activities of my lab and especially would like to tell you about why we are interested in studying computational quantum science. So the main, if you want, idea here is that, as also already expressed by Paul Dirac in 1929, is that while most of the fundamental equations that describe matter as we know it, also the matter at the human scale, I would say materials, molecules, are completely known, for example, Schrödinger's equation, these equations are, as Dirac was saying already in 1929, much too complicated to be solvable analytically, and we need to resort oftentimes, or in most of the times, to numerical approaches to solve them. So that's exactly what computational quantum science does. To understand the origin of this challenge, if you, for example, think about many-body quantum states, so the state of many interacting particles, interacting spins, electrons, for example, and if you look at the mathematics of this, so we know from the theory of quantum physics that the state of many of a composite system, for example, of n spins, as I've taught to most of you during the bachelor, is given by a linear superposition of 2 to the n basis states. For example, if I have an ensemble of spin 1/2 particles. And this vector, if you think about this vector in this very large state, is really contains a huge amount of information. And in practice, this means that, for example, if you want to numerically solve for these coefficients, for the amplitudes, when solving for Schrödinger's equation, or even in the time-independent or in the time-independent case, you are oftentimes limited to solving this for extremely small systems, where n is of the order of 20, 30, if you really make a strong computational effort. So the exact solution, numerical solution of this very important equation is strongly limited to small systems, and we need to, in order to go beyond this, we need to embrace new computational methods. So that's exactly what we do at CQSL, where we have two approaches to this challenge. So the first approach, both approaches, generally speaking, are dealing with variational state preparation, so what we call variational state preparation. So essentially, we try to prepare a state that depends on many parameters, so this psi w here, that approximates as much as possible our target solution, for example, the solution of the Schrödinger's equation. There are two cutting-edge approaches that we develop here at CQSL. So the first one, which is based on classical representation of variational states. By classical, I mean that this requires using classical computers, but we are still describing quantum systems. And then we have quantum variational states that instead require QPUs, or quantum processing units, in other words, quantum computers. And both approaches, however, are based on this idea of performing variational state preparation. So in the first approach that I developed in 2016, 2017, and it is based on the idea of representing neural network, of having neural network representations of many body wave functions. So essentially you have a neural network that computes for you the amplitudes of your many body wave function. And this is more broadly part of the applications of machine learning to physics. And for example, as we've also discussed in this review, this has been applied to many domains in physics, including quantum physics. And if you're interested, you can have a look at this review to see how many exciting developments of machine learning are happening in the domain of physics. So the other approach is about using quantum processors. So this is the famous Google quantum processors that was at the center of attention in 2019. And what we do here is that we want to prepare essentially quantum states that, for example, solve the Schrödinger's equation in a time-dependent and in the time-independent case. by tuning the parameters in the quantum circuit here. So before we were tuning the parameters in the neural network, here we tune parameters in the quantum circuits. Now, as you know, these are really exciting times to be a quantum mechanic, so a person working on quantum mechanics with his hands or her hands, essentially because there is really an exciting explosion of both experimental and theoretical activity in the field, and by learning these things firsthand, for example in my group, you would be able to apply and conceive even new ideas that could be extremely useful to improve the applications of these techniques to open problems in physics. If you are interested, let me also mention that I also have a course at the second semester of the first year in the master that is called Computational Quantum Physics, where you can learn also most of the methods that I mentioned and many others. If you're also interested in applying to be an intern for in my group, please write me an email, and especially it's important that you have a background in computational science, that you are really excited about doing computations and coding. It's certainly one pretty strong requirement for being able to enjoy at its best all the activities that we have in my group. So thank you for your attention.